Hi. I can see the audience tonight, so I can see also from the size of it, which last time was a black spot in front of my eyes, that there must be many of you here who are not thoroughly familiar with physics. And also a number that are not too versed in mathematics, and I don't doubt that there are some who know neither physics nor mathematics very well. That puts a considerable challenge on a speaker who is going to speak on the relation of physics and mathematics, a challenge which I, however, will not accept. I published the title of the talk in clear and precise language and didn't make it sound like it was something it wasn't. It's the relation of physics and mathematics. And if you find that in some spots it assumes some minor knowledge of physics or mathematics, I cannot help it. It was named... In thinking of the applications of mathematics to physics, it's perfectly natural that the mathematics will be useful when large numbers are involved in complex situations. Although, for example, if we took biology, the action of a virus on a bacterium is, if you watch it under the microscope, unmathematical. A jiggling virus finds some spot on this odd-shaped bacterium, and they're all different shapes, and finds some spot, and maybe it pushes its DNA in, and maybe it doesn't, and so forth. And yet, if we do the experiment with millions and billions of bacteria and viruses, then we can learn a great deal about the viruses by taking averages and working with large numbers. And we can use the mathematics involved in the averaging. We can see whether the viruses develop in the bacteria some new strains and in what percentage, and so we can study the genetics, the mutation, and so forth. To take another more trivial example, you know, imagine an enormous board, a checkerboard to play checkers, or drafts. And if the board is very large, the actual operation of any one step is not mathematical. It's very simple if it's mathematical at all. It either goes one side or the other on a diagonal, or it reaches and becomes a king and can go backwards when it reaches the end. In other words, the statement of the rules are very simple and do not really involve any mathematics. But you could imagine that on an enormous board with lots and lots of pieces, some analysis of the best move or good moves or bad moves might be made by a deep kind of reasoning which would involve somebody having gone off first and thought about it in great depth, and that becomes mathematics, this abstract reason. Another example is switching in computers. If you have one switch is either on or off, and there's nothing very mathematical about that, although mathematicians like to start there with their mathematics. But with all the interconnections and wires to figure out what a very large system will do, one requires a mathematics. And I would like immediately to say that a mathematics has its primary application, or it has a tremendous application in physics, in a discussion of the detailed phenomena in complicated situations, granting the fundamental rules of the game. And that is something which, if I were talking only about the relation of mathematics and physics, I would spend most of my time discussing. But since this is part of a series of lectures on the character of physical law, I do not have the time to discuss the applications of mathematics and physics to calculating what happens in complicated situations, but we'll go immediately to another question, which is the character of the fundamental law. If we go back to our checker game, the fundamental laws are the rules by which the checkers move. The mathematics may be applied in a complex situation to figure out what happens in the next move, what's a good move to make in a complicated situation, but very little mathematics is needed in the fundamental, simple character of the basic laws. Now, the strange thing about physics is that for the fundamental laws, we still need mathematics. For example, I give two examples, one in which we really do not and one in which we do. There's a law in physics called Faraday's law, which says that in an electrolysis, the amount of material which is deposited is proportional to the current and to the time that the current is acting. And that means that the amount of material is proportional to the charge which goes through the system. Sounds very mathematical. But what's actually happening is that electrons going through the wire each carry one charge. And to take an example, a particular example, it may be that to deposit one atom requires one electron to come. And so the number of atoms that are deposited is necessarily proportional to the number of electrons that flow, and thus to the charge that goes through the wire. So the mathematically appearing law has as its basis nothing very deep. requiring no real knowledge of mathematics, that one electron is needed for each atom in order for it to deposit itself. That's that's mathematics. I had to say number one. But it's not the kind of mathematics I'm talking about tonight. Now, if we take, on the other hand, Newton's law for gravitation, which has these aspects which I wrote down last time just to impress you with the speed at which mathematical symbols can carry information. We said that the force was proportional to the product of the masses of two objects and inversely is the square of the distance between them, and that bodies react to forces by changing their speeds or changing their motions in the direction of the force by amounts proportional to the force and inversely proportional to their masses. Now that's words, all right, and I didn't have to write the equation, but nevertheless it's kind of mathematical, and we would wonder, how can this be a fundamental law? How can this planet out there look, what does it do to it? It looks at the sun and it sees how far away it is, and it decides to calculate on its internal adding machine the inverse of the square of the distance, and that tells it how much to move. This is certainly no explanation of the machinery of gravitation. So you might want to look further, and various people have tried to look further. Newton was originally asked, it doesn't mean anything, it doesn't tell us anything. He says, it tells you how it moves. It should be enough I told you how it moves, not what. But people are often unsatisfied without a mechanism, and I would like to describe one theory which has been invented among others, of the type that you might want, that this is the result of large numbers. And that's why it's mathematical. And I give this theory, perhaps you've thought of it yourself. Every once in a while some student comes running in, he suddenly explains gravitation. Suppose that in the world, everywhere, there are flying through us at very high speed a lot of particles that come equally in all directions. They're just shooting by, and once in a while hit us in a bombardment. But we and the sun are practically transparent for them, nearly. But some hit, and so it's not completely transparent. Then look what would happen. If the sun is here, and the earth is here, then if the sun weren't here, there would be particles bombarding from all sides, giving little impulses by the rattle of these bang, bang, the few that hit, which would not shake the earth in any particular direction, because there is many coming from one side as the other, from top, from bottom. However, when the sun is here, the particles which are coming in this direction are partly absorbed by the sun because some of them hit the sun and don't go through. Therefore, the number that are coming from this direction toward the earth is less than the number that are coming from the other side, because here they have no opposition from no sun there. And it's easy to see, after some mental effort, that the further the sun is away, the less in proportion of all of the particles are being taken out of the possible directions in which particles can come. I mean, the solar size appears smaller. And, in fact, inversely is the square of the distance. So there will therefore be an impulse toward the sun on the earth that's inversely as the square of the distance, and is the result of large numbers of very simple operations, just hit one after the other from all directions. And therefore the strangeness of the mathematical relation will be very much reduced, because the fundamental operation is much simpler than calculating the inverse of the square of the distance. This machine does the calculating, these particles bouncing. Only trouble with it is that it doesn't work for other reasons. Every theory that you make up has to be analyzed against all the possible consequences and to see if it predicts anything else. And this predicts something else. If the earth is moving this way, more particles will hit it from the front than from the back. If you're running in the rain, more rain hits you from the front of the face than in the back of the head, because you're running into the rain. And so as the earth is moving in this direction, it's running into the particles, rather, and running away from the ones that are chasing it from behind, so that more particles hit it from the front than from the back, and there would be a force also sideways whenever there was any motion. This sideways force would slow the earth up in the orbit, and it certainly would not have lasted the at least 4 billion years that it has been going around the sun. So that's the end of that theory. Well, you say that was a good one, though. It got rid of the mathematics for a while. Maybe I can invent a better one. And maybe you can, because nobody knows the ultimate. But up to today, from the time of Newton, no one has invented another theoretical description of the mathematical machinery behind this law, which does anything else but say the same thing over again or make the mathematics harder, and at the same time doesn't produce some wrong phenomenon. I mean, they have, like this model does it, but it produces something which isn't true. So there is no model of the theory of gravitation today other than the mathematical form. If this were the only law of this character, it would be interesting and rather annoying. But what turns out to be true is that the more we investigate and the more laws we find and the deeper we penetrate nature, this disease, that every one of our laws is a purely mathematical statement in rather complex and abstruse mathematics. This is relatively simple mathematics. It gets more and more abstruse and more difficult as mathematics. And why? I haven't the slightest idea why. It is only my purpose in this lecture to tell you about this fact. In other words, it's my purpose in this lecture to explain, really, why I cannot satisfy you, if you do not understand mathematics too well, in trying to explain nature in any other way. It is the burden of this lecture, in fact, to just tell you the fact that it is impossible to answer honestly, the challenge of explaining in a way that a person can feel the beauties of the laws of nature without their having some deep understanding of mathematics. I'm sorry, but it seems to be the case. You might say, all right, then there's no explanation of the law. At least tell me what the law is. Why not tell me in words instead of in the symbols? Mathematics is just a language, and I ought to be able to translate the language. And in fact, I can. And with patience, I think I partly did. I could go a little further and explain more detail that this means that if it's twice as far away, the force is 1/4 as much, and so on, and can convert all these into words. I would be, in other words, kind to the layman, as they all sit, hopefully that you will explain something. And various different people get different reputations for their skill at explaining to the layman, in layman's language, these difficult and abstruse subjects. The layman then searches for book after book with the hope that he will avoid the complexity which ultimately set in even by the best expositor of this type. He reads the things hoping one after he finds, as he reads, a generally increased confusion, one complicated statement after the other, one difficult to understand thing after the other, all apparently disconnected from one another, and it becomes a little obscure, and he hopes that maybe in some other book there's some explanation the man almost made it, you see. Maybe another fellow makes it right. And I don't think it's possible because there's another feature. Mathematics is not just a language. Mathematics is a language plus reasoning. It's like a language plus logic. Mathematics is a tool for reasoning. It's in fact a big collection of the results of some person's careful thought and reasoning. By mathematics, it is possible to connect one statement to another. For instance, I can say that the force is directed toward the sun. I can also tell you, as I did before, that the planet moves so that if I draw a line from the sun to the planet and draw another one at some definite period, like 3 weeks later, the area that's swung out by the planet is exactly the same as it will be in the next 3 weeks and the next 3 weeks and so on as it goes around the sun. Now, I can explain both of those statements to you carefully, but I cannot explain why they're both the same. So that if you don't appreciate the mathematics, you cannot see that the great variety of facts, the enormous apparent complexity of nature with all its funny laws and rules, each of which have been carefully explained to you, are really very closely interwoven. That logic permits you to go from one up to the other. It may be unbelievable that I can demonstrate that equal times will be swept out if the forces are directed toward the sun. And just to, if I may try, I will show you one demonstration to show you that those two things really are equivalent. And so that you can appreciate that there's more to merely the statement of the two laws, that the two laws are connected such that reasoning alone will bring you from one to the other. And the mathematics is disorganized reasoning, and that it's good to know how to do that, so to appreciate the beauty of the relationship of the statements. So I'm going to prove, if I may, the relationship that if the forces are directed toward the sun, that the equal areas are swept out in equal time. So we start, here's the sun, and we imagine that at a certain time, let's say the planet is here, and is moving in such a way that, let's say 1 second later or 1 hour, pick any time, let's say 1 second later, it's moved in such a manner that it has gotten to the position 2. Now, if the sun did not exert any force on it, then by Galileo's principle, it would keep right on going in a straight line. So in the same interval of time, later, the next second, it'll move exactly the same distance in the same straight line to the position 3, were there no force. All right, now first we're going to show that if there's no force, equal areas are swept out in equal time. I remind you that the area of a triangle is half the base times the altitude, and that the altitude is the vertical distance to the base. And that if the triangle is sort of cockeyed, there's a name for it which I forget, obtuse, then the altitude is this vertical height here. See, I know about the triangles, I just don't know the names. Now let us draw the lines to these 2 points in the case that there was no motion whatsoever. The question, this doesn't draw very well, I'm not accurate. But these 2 distances are equal, remember. The question is, are these 2 areas equal? Well, consider the triangle made from the sun and the 2 points 1 and 2. It's this one. What's its area? It's this space multiplied by this height. And what about the other triangle, which is the triangle in motion from 2 to 3? It's this base times the same altitude. The 2 triangles have the same altitude and, as I indicated, the same base and have the same area. So far, so good. If there were no force from the sun, equal areas would be swept out in equal times. The 2 triangles have equal areas. But there is a force from the sun. And during this interval, from 1 to 2 to 3, the sun is pulling and changing the motion in various directions, this way, that way. To get a good approximation to that, we'll take the central position or average position here and say that the whole effect during this interval was to change the motion by some amount in this direction toward the sun. That means that although the particles were moving this way and would have moved this way in the next second, because of the influence of the sun, the motion is altered by an amount that's poking in this direction. That's parallel to this, exactly parallel. These lines are parallel. It's the direction in which this new motion is. The new motion is a compound of what it wanted to do and the change that's been induced by the action of the sun. So it doesn't really end up at position 3, but rather at position 4. So now we would like to compare, it's getting complicated in the diagram, the triangle 2,4S and 2,3S. I'll show you that those are equal. Because they have the same base, those 2 triangles, this one here, and the one that happened when we had no force. The one with force and with no force have the same base. And do they have the same altitude? Sure, because they're included between parallel lines, and so they have the same altitude. And thus the area of the last triangle I drew is the same as the second one I drew, this 1, 2, 3, and that I had proved earlier was the same as the first one. So in the actual orbital motion of the planet, the area of the first, in second, and in the second are equal. So by reasoning, we can see a connection between the force, the fact that the force is toward the sun, and that the areas are equal. Not ingenious, no? This was, I borrowed this from Newton. It comes right out of the Principia, diagram and all. The letters are different, that's all, because he wrote in Latin. These are Arabic numerals. But incidentally, Newton made his proof geometrical like this, and made all his proofs in his book geometrical of this type. Today we don't use that kind of reasoning. We use a kind of analytic reasoning with symbols, which this kind of reasoning requires an ingenuity to draw the right triangles, the correct triangles, I mean, to notice about the areas and to figure out how to do it. You have to be clever. But there have been improvements in the methods of analysis so that one can be quite more stupid. And I write much faster, you're much more efficient then. And I want only to show what it looks like in the notation of the more modern mathematics, where you don't do anything but write a lot of symbols to figure it out. First, we would like to talk about how fast the area changes, and we represent that by area dot. And the area changes because of when the radius is swinging, it's the component of velocity at right angles to the radius times the radius that tells how fast the area changes. So this is the component of the radial distance multiplied by the velocity or rate of change of the distance. Now the question is whether the rate of change of area itself changes. The principle is it's not supposed to change. The rate of change of area is not supposed to change. So we differentiate, so-called, this again, and we put, that'll mean some little trick about putting dots in the right place. And that's all. You have to learn the tricks. It's just a series of rules that people have found out that are very powerful for such a thing. And this says the component of the velocity at right angles to the velocity. It is none. There is none. The velocity is in the same direction as itself. And the acceleration, which is this thing, the second derivative, or the derivative of velocity, is the force divided by the mass. So this says that the rate of change of the area is the component of force at right angles to the radius. But if the force is in the direction of the radius, as Newton said, then there's no force at right angles to the radius, and that means that the rate of change of area doesn't change. I just wanted to illustrate the different kinds of notation. Now, Newton knew how to do this, more or less, with slight different notation, but he wrote everything this way because he tried to make it possible for people to read his papers. He invented the calculus, which is this kind of mathematics, and is a good illustration of the relation of mathematics to physics. When the problems in physics get difficult, we may often look to the mathematicians who have already studied such a thing and have reasoned about such an item before and have prepared a line of reasoning for us to follow. On the other hand, they may not have, in which case we have to invent our own line of reasoning, which will then pass back to the mathematicians, because everybody who reasons carefully about anything is making a contribution to the knowledge of what happens when you think about something. And if you abstract it away and send it to the Department of Mathematics, they put it in the books as a branch of mathematics. Mathematics, then, is a way of going from one set of statements to another. It's evidently useful in physics because we have all these different ways that we can speak of things, and it permits us to develop consequences and analyze the situations and change the laws in different ways and to connect all the various statements. So that, as a matter of fact, the total amount that a physicist knows is very little. He has only to remember the rules for getting from one place to another, and he's able to do it then. In other words, all of the various statements about equal times, the forces in the direction of the radius, and so on, are all interconnected by reasoning. Now an interesting question comes up. Is there some pattern to it? Is there a place to begin fundamental principles and deduce the whole works? Or is there some particular pattern or order in nature in which we can understand that these are more fundamental statements and these are more consequential statements? There are two kinds of ways of looking at mathematics, which for the purpose of this lecture I will call the Babylonian tradition and the Greek tradition. In Babylonian schools in mathematics, the student would learn something by doing a large number of examples until he caught on to the general rule. Also, a large amount of geometry, for example, was known. A lot of properties of circles, theorem of Pythagoras, for example, formulas for the areas of cubes and triangles and everything else. And some degree of argument was available to go from one thing to another. Tables of numerical quantities were available so that you could solve elaborate equations and so on. Everything was prepared for calculating things out. But Euclid discovered that there was a way in which all of the theorems of geometry could be ordered from a set of axioms that were particularly simple. And you're all familiar with that much geometry, I'm sure. But the Babylonian attitude was, if I make my way of talking what I call Babylonian mathematics, is that you know all these various theorems and many of the connections in between, but you've never really realized that it could all come up from a bunch of axioms. Modern mathematics, the most modern mathematics, concentrates on axioms and demonstrations within a very definite framework of conventions of what's acceptable and not acceptable as axioms. For example, in geometry, they take something like Euclid's axioms modified to be made more perfect and then to show the deduction of the system. For instance, it would not be expected that a theorem like Pythagoras' that the sum of the squares of the areas of squares put on the sides of the triangle will equal the area of a square on a hypotenuse should be an axiom. On the other hand, from another point of view of geometry, that of Descartes, the Pythagorean theorem is an axiom. So the first thing we have to worry about is that even in mathematics, you can start in different places. Because of all these various theorems are interconnected by reasoning, there isn't any real way to say, well, these on the bottom here are the bottom, and these are connected through logic. Because if you were told this one instead, or this one, you could also run the logic the other way if you weren't told that one, and work out that one. It's like a bridge with lots of members, and it's over-connected. If pieces have dropped out, you can reconnect it another way. The mathematical tradition of today is to start with some particular ones which are chosen by some kind of convention to be axioms and then to build up the structure from there. The Babylonian thing that I'm talking about, which I don't really not Babylonian, but it's to say, well, happen to know this, and I happen to know that, and maybe I know that, and I work everything out from there. And tomorrow I forgot that this was true, but I remembered that this was true, and then I reconstruct it again, and so on. I'm never quite sure of where I'm supposed to begin and where I'm supposed to end. I just remember enough all the time so that as the memory fades and the pieces fall out, I put the thing back together again every day. The method of starting from the axioms is not efficient in obtaining the theorems. In working something out in geometry, you're not very efficient if each time you have to start back at the axioms. But if you have to remember a few things in the geometry, you can always get somewhere else. It's much more efficient to do it the other way. And what the best axioms are not exactly the same, in fact are not ever the same, as the most efficient way of getting around in the territory. In physics, we need the Babylonian method and not the Euclidean or Greek method, and I would like to say why. The problem in the Euclidean method is to make something about the axioms a little bit more interesting or important. But the question that we have is, in the case of gravitation, is it more important, is it more basic, is it more fundamental, is it a better axiom to say that the force is directed toward the sun, or to say that equal areas are swept in equal time? Well, from one point of view, the forces is better, because if I state what the forces are, I can deal with a system with many particles in which the orbits are no longer ellipses because of the pull of one on the other, and the theorem about equal areas fails. Therefore, I think that the force law ought to be an axiom instead of the other. On the other hand, the principle that equal times are swept out in equal areas are swept out in equal times can be generalized when there's a system of a large number of particles to another theorem, which I had prepared to explain, but I see I'm running out of time. But there's another statement which is a little more general than equal areas in equal times. Well, I have to state what it is. It's rather complicated to say, and it's not quite as pretty as this one, but it's obviously the son of this one. I mean, it's the offspring. If you look at all these particles, Jupiter, Saturn, the sun, and all these things going around, lots of stars or whatever they are, all interacting with each other, and look at it from far away and project it on a plane, like this picture, then everything is moving this way, and moving that way, and so on. Then take any point at all, say this point, and then calculate how much each one is changing its area, how much area is being swept out by the radius to every particle, and add them all together. But wait, those masses which are heavier count more strongly. If this is twice as heavy as this one, then this area, it counts twice as much.